Welcome back, and welcome back to our graph. Again, we are going to continue looking at this function and look at one more interesting property of functions and their graphs, and it has to deal with this word up here, concavity. Okay, and so, well, before we get there, let's just kind of summarize. So what we know right now is that we talked about where it's increasing, decreasing, constant, and then with those talked about rates of change, right? And then we talked about extrema, right? We said it as local extrema of a maximum of 0 and an absolute and local extrema at -1 at plus and minus 1 for x. Okay, so we know all that. What more could we possibly need? And it's this idea of concavity. Okay, and so I'm going to let you, if you need to pause the video, read the definition. Okay, concavity is just in general, it talks about the bendiness of a function. And so if we talk about it formally with mathematics, we have to get into calculus. We talk about a second derivative, okay, whatever. And so what we do is we interpret this as the rate at which the rate of change is changing. Parse that one in your brain a little bit. The rate at which the rate of change is changing. So if we're increasing, if we have like a positive slope, is the slope becoming more and more positive or less positive? Um, Similarly with a negative slope, is it becoming more or a larger negative number or a smaller negative number? Okay, that's the idea of concavity. We're looking at how the slope changes as we move along the function. And so if we have a function that's concave up on an interval, what we would see on that interval is it's bending upward. And so here's kind of the nice little picture definition that I like to use instead of words sometimes. But if it's concave up, it makes a bowl that you could fill with soup or water or a liquid, right? A concave down function would look like a hat, like you could put this on somebody's head, or it would be a nice umbrella, okay? And then you can have certainly functions that are both concave up and concave down. So we have an example of that. And when it changes concavity, at that point where it changes concavity, we call that an inflection point or a point of inflection. Tomato, tomato, depends on what order you want to put the words in. But these are the central ideas of concavity, okay? And so what we're going to do is just kind of look at this and inspect it. This is not going to be precise at all. To do it precisely with algebra, we need A, the equation of the function, and B, we need calculus. So we are just going to do our best to eyeball this thing, okay? So I'm interested in where this is concave up, cave up, where it is concave down, down, and if I have any points of inflection, okay, poi, not a person of interest, okay. Good TV series if you haven't watched it. Concave up, concave up. So where does it look like you can put a liquid in and it'll stay in there as a roughly a bowl shape? Okay, I'll do this in yellow highlighting. Well, this is kind of maybe up to interpretation, but I would say it's kind of this segment in here, right? So I'll highlight it a little bit better. So right in there. And then right in here, if I don't want that in yellow, I want that in green. If I look where it's concave down, it would switch concavity right in here because that looks like a hat. I could put that on and it would stay on my head. And then after this place, it would switch to being concave up again. Okay, so when we talk about concavity, these are intervals as well, so we need to use interval notation. And again, just like intervals of increase and decrease, it is improper to talk about increasing and decreasing at a point because we need that region, right? And so for the same reason, talking about bendiness, we don't talk about a point as being bendy, right? So we always use open intervals for concavity. So the interval that we have here would be minus infinity for this first part, all the way up until, so I'm coming left and I'm getting stuck right here. And according to my scale, if this is -1, that would be about -1/2. And then the other region would be from about 1/2 to infinity. Okay, so using interval notation for that. And then concavity would be precisely in between. So -1/2 to 1/2. okay? And the points where it transitions from concave down to concave up, again, that's our point of inflection. And so what we would write these as is literal points. So these are points, not intervals, okay? So I know with concavity we use interval notation, but points of inflection are literal like XY points. So I would say here that this would be, you know, -1/2, comma, well, to make it simple, I might do f of -1/2, which actually looks to be about -1/2. And then the other point would be +1/2, comma, whatever the function is at 1/2. Again, based on this scale, if this is -1, both the y values here seem to be about -1/2. Okay, but so concavity again, where's it bending? And if it's bending up to make a bowl, concave up there, and then if it's bending to make a hat, concave down. And if it switches, point of inflection. All right, so here we go. And so here's our other example that we saw before. We did not discuss concavity, so I want you to pause the video, see if you can identify where it is concave up, concave down, and where points of inflection are, if there are any. There could be none, okay? So identify those three things, resume the video when you're ready. Here are my approximate answers. Again, this isn't, since I am eyeballing it, you know, you might have slightly different things. But if I look where it's concave down, I see that here, right, it's a hat that I could wear. And then I said it kind of stopped being concave up about there. And then it switched concavity, so that's my point of inflection, at this place, and then changed to concave down thereafter. Oops. So, or sorry, I have these backwards. My bad, my bad. This is concave up, and this is concave down. Okay. So let's finish that there. So we have concave up on 1 to 4. Again, interval notation, concave down, -infinity to 1. Again, interval notation, and then point of inflection where it changes. Okay. So there we go. We have points of inflection as well as concave up, concave down, ready to add to our arsenal of function properties based on their graphs.